Hello everyone and welcome to the Autodesk Robot Structural Analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. In this video, we are going to discuss how Autodesk Robot calculates the provided reinforcement for beams. So to start with, I'm going to select my 2D frame design. Now I am in my 2D frame design GUI. Of course, this environment has been explained before in a video about understanding the GUI of Autodesk Robot. Please feel free to check this out. So I have my beam, and my beam is going to be a two-span beam. The first span is 5 meters, the second span is 6 meters, and well, I'm just going to define me a beam. Before I start, however, since I'm going to design stuff, it's worth it to mention that I'm going to design my structure using the ACI code. So I'm just going to click on the wrench tool, go to my job preferences and double check that. Of course, checking job preferences was explained before in yet another video that is once again linked above, but I'll just quickly go through it very fast. So for my materials, I'm going to use American materials because I'm designing using the ACI code, which is the American code. Feel free to add any material or change that database according to your design code. I'm designing using the ACI code, so my materials are going to be American. For the design code, I'm designing using ACI 318 metric, and this is the latest design code in Autodesk Robot for the ACI. Maybe in the future they will add the 2018 edition. For databases, there is something called steel reinforcing bars, and I'll make sure that I'm selecting the metric and clicking the current database here because I'm a metric guy and I want to design my reinforcement according to the metric reinforcing bars. The difference being that in the metric, the bars are named by their diameters, whereas in the imperial, or the diameters have numbers. So right, everything seems to be nice, so just click OK and start modeling my beam. Of course, modeling the beam was covered in a previous tutorial. For me, I'm going to model a reinforced concrete beam with a cross-section of 350 by 500. The cross-section was chosen according to the ACI code. The ACI code states that you can skip the deflection calculations if you choose a beam that has a height which is stipulated in the ACI code. In my case, my two spans are at one end continuous, and my height of the beam should be L over 18.5. 6 meters over 18.5 is less than 500 millimeters, so I'm more than satisfied with this. And this beam should satisfy my deflection control, which means I don't need to control my deflection for this beam because I'm following the ACI code suggestion. Alright, so I have my beam now. I'll just support it very quickly. I'll add me some pin supports, and I'll add me two load cases, one dead, which will include the dead load, and one live, which will include the live load. The dead load has already pre-calculated in it the self-weight. You can double check this using the load table. This was also explained in the previous video that is going to be linked above. Alright, so for my dead load, I'm assuming that my load per unit area is 10 kilonewtons per meter square, and that the beam has a tributary width of 5 meters, which means that in the dead load, my beam is going to have a 50 kilonewton per meter dead load. In the live load, I'm assuming a 3 kilonewton per meter square live load on the plate, so my beam is going to have 15 because it has a tributary width of 5. Fantastic. So if I run the analysis now, quickly go to results, diagrams for members, check MI, click OK. You can see I have bending moment diagram, I have nothing wrong, so everything seems to be fine. Fantastic. So let's take this beam and click on design. Now, I have explained required reinforcements in the video before, which is once again linked above, but for today I'm going to check the provided reinforcement of reinforced concrete elements. Difference being that here robot calculates the area steel required and you are responsible for distributing this area steel required, and the other option, robot distributes the reinforcement for you, which will take a little bit more details. I click on that. Now robot will start importing the structure. You can import the loads based on the combinations or in simple cases. I am using simple cases because I want robot to perform the combinations for me as well as perform the load, the live load case of loading, meaning that it is going to variate the live load on all the spans. Alright, fantastic. So I have it right now. I'll just once again click on OK. So now I am in my design view. Now I have imported my beam as well as my foundation because it seems robot thought that my pins are actually foundation. I'm going to talk about my beams today. So I'll double click on my beam, which opens the beam design GUI, and it seems I have a problem that I don't see my beam. Now if you have the same problem, you click on this little window button and drag this to the side, and now you can see everything, because now you can see your beam and you can see your inputs. Now you are in the input section of your design. You can see that there are multiple options here. Those options are with regard to your beam, and we are now in the input and the geometry input of my beam. Now first of all, my span geometry has a lift support, and now we need an assumption. I'm assuming that my column has a width of 50 or 0.5 meters in the plane of the beam. So I'll just do that very quickly. All right, fantastic. Now there are some more things for segment. If you want to change stuff, like if you want to have a beam that is inclined or something, you can use this for staircases if you want, especially this one. I will not do anything because here this is only an introductory video. I will talk about staircase design later, but for now I just keep it as simple as possible because there is a lot of stuff to be covered. All right, so now if you do a quick blind calculation, everything is not going to work. Let's take a look. You will be bombarded with millions of errors, which will basically, first of all, put you off. But let's dissect those errors one by one. You see, you have 4 errors related to the design capacity and 1 error related to the environmental conditions or the service limit state. And well, the first good news is that the deflection does not satisfy code requirements. Nobody cares about this because we have assumed the height of the section conforming to the ASI code, and in that case the ASI code actually tells you that you need not check deflections because this height is satisfying and good. But well, I still have a lot of other problems, and those are really dangerous. I have capacity and design problems, which means that the beam I have now is not able to hold or withstand the forces applied. Now, if you click on any one, it tells you that, for example, the bending moment has a problem. Now, how do I see this? Well, let's forget about the errors for a second and look at something called beam diagrams. If you click on that, you see the bending moment diagram of the beam. Now, the green line here is the applied bending moment on the beam, whereas the red here is the ability of the beam to resist. And you can see that near the support, the green is larger than the red, which means that the applied forces are larger than what the beam can carry, and that's the reason why you get an error and a warning for this. So yeah, this is the first problem. And let's take a look on the shear. The shear seems to be fine. No, there is a problem here. You can see here, green is more than red, which is basically a problem. You can also switch from ULS to deflection, and now you can see that, well, for the first span, deflection is satisfied. For the second span, deflection is not satisfied. The second span was 6 meters, so it's basically makes sense not to be satisfied. Now, the limit of deflection that was imposed here is a limit from Autodesk Robot, which is 25 millimeters. Now, each code has its own limitation because usually the code limits the deflection according to a fraction of the span, for example, L over 180, for example. I just leave it as is because for my deflection control, I am abiding by the ASI code requirement that says if you are using L over 18.5 as a height for the beam, then you are on the safe side and you do not need to check the long-term deflections. And by the way, this beam fails not for the short-term deflection. The black one is the short-term deflection. No, it fails in the long-term deflection that actually includes creep and includes all kind of stuff. And please notice that for the long-term deflection, different ACI limitations apply rather than the short-term deflection. And you can check this out in the ACI code. For example, it says that L over 240, I think, is what is the limitation for a beam if it's not holding anything that is deflection sensitive from live load only. So yeah, there is a lot of details to be covered here. I'm not going to cover this because I'm abiding by the ACI code recommendation. Okay, so I have a problem with my reinforcement basically because it cannot carry it. You can see that if you go back to your ULS, once again, you have a problem here. Now, what is actually the problem? The problem is that if you go to beam reinforcement, you cannot see anything, so I'll just make this smaller and drag it here. If you go to beam reinforcement and basically like zoom in just to see stuff, you can see that there is all kinds of strange reinforcement happening here. And if you run the calculation again, it actually tells you where the steel is that has problems. So if you click, for example, on this, click on select rebars, it selects you the rebars that have problems. All right, so let's dissect this. Now, first of all, what is this? Why is this not continuous? This is the first question. The second question is, what are those steel bars? I mean, I see a lot of steel bars. This is not how my steel looks in real life. Like, I have less than this. And I mean, it doesn't look right. Like those reinforcements don't seem to be right. So there is a lot of work to be done here, and it needs some time. So the things I'm going to cover is not this, because this is like the reinforcement templates that you can change. I will actually go into the deep depths of the reinforcement itself. So the first thing you have here is story parameters, which has nothing to do with the error. The only thing that you can change here is the sustained load action 4. This changes the long-term deflection calculations, because according to the definition, the long-term deflection calculations includes creep, and creep is measured after an X number of months. In this case, it's 5. Now, I don't care because I'm using, once again, the ASI recommendation. For calculation options, this is where the fun starts. Now, first of all, for the first side here, you have deflection calculations, and you can correct the deflection, i.e. solve the problem of deflections by changing either reinforcement or geometry. I'm not gonna touch this because, as we have agreed, I am abiding by the ASI recommendation. Section optimization, geometry optimization provides robot with the ability to change your width and height, because remember, our width is 350 and the height is 500. You can actually allow robot to move those and change those heights to fit your design. I will not do that, because usually the height of the beam is based on some architectural and other factors, so I rather let myself change the sections rather than letting robot do it automatically. The cover is measured from the transversal reinforcement. That's perfectly fine. Now, of course, the cover can be changed. You can fix your cover based on what the code requires from you. I will leave it as default like this. For my concrete, I'm going to select me a concrete that is almost 30 megapascals. Of course, you can switch any concrete you want. My concrete is not lightweight concrete, so there is no lambda modification factor. If it's lightweight, you open it and change the lambda. This is provided by the ASI code. Also notice, you can see in the title that those options are from the ASI code, so which means that you can see different things if you have different codes. For longitudinal reinforcement, which means main reinforcement in the longitudinal direction, those are the bars that robot is going to use, and this is the grade I will be using. Transversal reinforcement. Now, I like to use the same grade for both longitudinal and transversal reinforcement, so I'm using the 420 megapascal steel. Additional reinforcement, which is the construction reinforcement, is also 420 megapascals. So just click on OK. Now, if you run the analysis, the only thing that changed is some reinforcement grading, but it will not work because if you click Run, you can see that, well, my errors are not really getting better. Now, well, one of them seems to have disappeared, which is the shear capacity. I think it disappeared because I have increased the shear strength of my transversal reinforcement, and this seems to have solved one of the problems. But, well, it's not really an effective solution because I still have my 3 problems. However, we still have this to talk about, which is reinforcement pattern. Now, the first thing is that my reinforcement is not going to be span by span. I want it to be whole beams because I want my reinforcement to extend to the other span if it can, because each straight bar has a maximum length. So if it's possible to apply 1 bar for the entire beam, why not? So I will have it to be my whole beam. For the main reinforcement, there is a minimum diameter of 30 millimeters. I don't care, you can select anything you want, because robot will actually suggest a different diameter if it needs to do that. There is also the bar spacing, minimum and maximum, and also spacing for longitudinal reinforcement for torsion. You can check that. Tied all means that all the reinforcement in the cross sections have ties around it. While this is not the case, I want it to be automatic because the ASI code allows you to tie 1 bar and leave 1 other bar untied if the distance between them is less than, I think, 15 centimeters or something. I don't remember actually. For bottom reinforcement, this is where the fun starts. You can control the number of layers, the diameter, and the number of bars in a layer. So first of all, I will leave it as is. I will only increase the number of layers to 4 just to allow it to increase the layers if need be. Also, the layers are going to be determined automatically, which means robot will try 1 layer, 2 layer, 3 layer, and 4 layers. For top reinforcement, I don't want it to be as bottom reinforcement because they are substantially different, and I want my layers to be 4 done automatically. And you can see that there are diameters, and there is a hidden problem here. You see, if you go to diameters, I'm not changing anything actually. But if you go to top reinforcement, you see that the diameter is as bottom reinforcement. I don't want that because usually the top moment is different than the bottom moment, so I think it makes sense that my diameters should be different. For transversal reinforcement, I will keep it as is. I'll come back to it later. And for construction reinforcement, I will leave it as is. I'll come back to it later because I want to solve the problem step by step. So if you calculate now, it will not solve the problem. There seems 1 problem less, and there seems it's almost solved, almost, but not really. So if you go to the diagrams, you can see that it is almost so, but not really. Here you have a 1% difference. It's really it's really annoying, but well, it's not safe. And if you go to beam reinforcements and take a look, it seems that things look okay-ish. However, I have two problems. The first problem I have with this reinforcement is this little tiny things. Now, what are those? What's the meaning of this? What are those bars? Those bars are actually called assembly reinforcement. If you click here, you can see that if you click on a bar, it will highlight you the bar. It's called assembly reinforcement, and you have assembly reinforcement in top and assembly reinforcement in bottom if need be. There's a strange thing about assembly reinforcement. The strange thing about assembly reinforcements is that this reinforcement is by default not taking into account when calculating the strength of the beam, which is a shame because I mean it's there. Why not use it? So to change that, you can go to once again reinforcement pattern, to the construction reinforcement, which is called assembly by the way. You can see that you can actually click on consider the assembly reinforcement in load capacity calculations. So that's fine. If you click on that, it will work, but there are still more improvements to be done. Now, the assembly reinforcement now is used in the strength calculation, and that's why suddenly the main reinforcement that was here disappeared. So, okay, it seems to make sense to use the assembly reinforcement because why not? It's there. Now, the second thing is that it seems my assembly reinforcement is really small in comparison with my main reinforcement, and this creates practical problems because usually you like to have at least your top reinforcement alone to be at least of the same size and the bottom reinforcement alone to be at least of the same size if you can. Now this size variation would cause practical problems, so actually I can change this by going to construction reinforcement and clicking on the diameter is as for main bars. So now my assembly reinforcement is going to have the same diameter as my main reinforcement. And you can see that, well, it starts producing meaningful drawings, but I mean, look at this. This is too much. This steel is, I don't know how we even can cast this. This is not practical. I mean, take a look here. This is too much. So there are still problems, and I'm solving it step by step. So the capacity in the bending is still not sufficient, and there is one last trick why this is the case. So allow me to show you this. So if you go to reinforcement pattern, now go to bottom reinforcement, go to the number here, you can see that the number is between 2 and 8, and robot tries to match the number of the bottom reinforcement with the number of top reinforcement, which is something I don't like. So I first of all change the minimum number of bars to 4 to have a twofold effect. The first effect is I want to reduce the size of the bar. The second effect is I want to allow robot to add more bars on the top. So if I click on that now and calculate, you see, well, everything seems to be working perfectly because now I have no problems. If you go to beam diagrams, you can see that everything is working in perfect order. So yeah, I have just accomplished my design. But I mean, I'm a perfectionist, so there is still a problem. Well, okay, the bars seem to be okay-ish. I don't know. There are too many bars. I don't know, maybe I should decrease the number of layers because now I'm doing only improvements to this. So I think number of layers is too much. I'll just change that. So I'll just go to reinforcement patterns once again, go to my top reinforcement and just make 3 layers, for example, and just hit OK and try again. So you see, this is some sort of repetitive task that you will have to continue doing until you finally get this. Now you have 3 layers, and robot actually increased the bar size to match those layers. Now I will leave this for you to investigate. You can actually even change the diameter of the bars. I mean, look, the top is 30 millimeters and the bottom is 25. I mean, you can actually unify the diameters if you want. So to bottom reinforcement, to diameter, I can match it to become as bottom reinforcement. I'll just click on OK. Maybe this would be better. Now, you see, I'm just doing some minor improvements. The best way of learning those things are just to keep changing stuff and getting a feeling of what those things are doing. What is the effect of those things. You can even force robot to use 25 millimeters and run the analysis. And now it's 25 millimeters everywhere. And now I think I like it because now it's only one layer of steel bars. All right, so I mean, you can play around, and I think I have reached a beam that I kind of like, but there is one problem left. The problem that I have now is with stirrups. It seems that, look, here you have a spacing, here you have a different spacing, Here you have a different spacing. I mean, this is nice and dandy, but it seems that my stirrup spacing is not even to the closest 5 centimeters, which causes practical problems. Trust me, I have seen a lot of stirrups that cause confusion among the workers. So usually and this is a personal opinion, I usually like my stirrups to be 5 centimeters spaced, like 50 millimeters, 100 millimeters, 150 millimeters, and so on. So I will change that. Now, how do I change my transverse reinforcement design? Well, I go to reinforcement pattern, to my transverse reinforcement, and I don't want it to follow the envelope exactly. I want it to like just design each 1 meter segment alone, and I want my spacing to be to the closest 5 centimeters. Now, this might break my analysis. I don't know really. I just try this right now. Hit the OK button, analyze again. So I hope that my beam, yeah, it works perfectly. Now those are, you can see that there are just 2 spacings. There is one spacing, it seems it's 5 centimeters or 10, I'm not really sure. And the other one is 20, it seems. So yeah, now I am happy and I think my beam is perfectly designed. I can start looking at my calculation sheet and export me some drawings. If you go to beam note, now it will still tell you not OK because of the deflection, but nobody cares. I can quickly hack that. I will hack that because I told you that I am conforming with the ASI code, which allows me not to check any deflection if I abide by the minimum beam height. So I just go to my general here and just tell him, hey, listen, man, I don't care what your deflection is, even if it's 100 millimeters, I don't care because I'm abiding by the ASI code recommendation. So now no errors. This is a hack, by the way. That's not a solution. So if you go to beam note, now you see that the section is okay. How can you read this? Well, it tells you some information about the beam itself, about the material used, about the spans, and about the calculation options you're choosing. Now the cover is 50 millimeters depending on the code. You can force it to change if you want. I will leave it as is. You can see that the internal forces are being covered perfectly by the reinforcement, and that it satisfies also the reinforcement requirement, which is the required reinforcement. And finally, I just skipped too much. You can even see that the beam is calculated by different points, and it shows you that for all those points, the reinforcements are able to carry the required forces. And finally, and this is really important, you get a quantity surveying, and this is what I love in Autodesk Robot. It gives you a quantity survey of what you need, and this is basically what you will use to buy the stuff you need. So you see that for concrete, it's 2 cubic meters. The formwork, which is the side area, is 15.35 meters square. The steel required, the total weight is 361. Now the density is something I really love and like because usually I use this in estimating the required steel. Now this has nothing to do with Autodesk Robot, but whenever I work on contracts, you see that in bill of quantities in those contracts, it tells you to like basically provide, I don't know, like 30 cubic meters of reinforced concrete for beams, and it never tells you how much steel you have in those beams. Now, usually I know that for beams, your steel is between 150 and 250 kilograms per meter cube, so I see that this is perfectly fine. And you can see that you have a list of shopping, or a shopping list basically, which gives you a fine diameter, it gives you the length, it gives you the number of pieces and the total weight. Allow me to give you some practical advice here. Those lengths are produced by the machine, which gives you some strange 1.42 meter steel bar length. Now, depending on the country where you're working, some countries, every centimeter is perfectly fine. Like you can ask a steel manufacturer to provide you with a steel bar of 1.333 meters if you want. Now, this is in some countries. I don't know. In the countries where I worked, usually steel is cut into lengths that make sense, like 1 meter, 1.5, 2 meter, 3 meter, 4 meter. And the criteria here is that you cut your steel bar into lengths that are able to be divided. Meaning, if your steel bar is 12 meters from the manufacturer, you should divide it into pieces that are able to be cut without any excess. For example, if you choose to cut your steel bars to 5 meters, if you have a 12-meter bar, this means that you can only produce 2 pieces 5 meters from your 12-meter bar, and you will have an excess of 2 meters, and you need to think where you should put those 2 meters to avoid any loss of steel. This gets doubly important if you have excesses less than 1 meter, because it becomes really hard to use this excess anywhere, so it becomes a waste. What I'm trying to say here is that as a designer, you should always double check your lengths before you provide any tables and modify them to make more sense of this. Speaking of tables and drawings, well, you can actually produce some drawings by clicking on the drawing button. If you click on this button here, if you click on that, you can start seeing the drawings of your beam. Of course, this is not the full beam, this is only one span, and you can select the next span and the previous span from those two arrows, and it seems everything to be fine. You can of course click File and export this, or save it in a different format and export it as DXF for your AutoCAD. And you can see this is really nice. It tells you each bar with a number and tells you what the length of the bars is. Now here is where your human intervention is required, because sometimes the bar's length doesn't make sense, so you would add a little bit length to it to make sure that it makes sense. You can see also that the stirrups are here placed. The first stirrups are at 10 centimeters. It seems that the units here are in centimeters. I'm surprised. I think I have asked it to be in meters, but it seems that those units are in centimeters. I really don't know why. I think I would check out why this is the case. Anyway, you have 13 stirrups at 10 centimeters and 21 stirrups at 20 centimeters. You can actually modify this by clicking on this button, which is Drawing Components. And now you can click on any component and modify it. So for example, this DD section is taken here. If you click on that DD section, you can actually choose where this section is taken. So if you click here, which is called Section Location and Scale, you can move the section DD from any position you want, for example here. And you can change the scale if you want. You can add a different scale if you want. I just leave it as is. But I just moved my section here. If you click on OK, you can see that DD has been changed and that the section is now here. This CC section, it's taking perfectly because you see all the bars. I mean, yeah, those are a lot of options you can play with, and that's it. That's everything I wanted to talk about today. This is how Robot provides reinforcement. It's really a nifty and nice tool, and there are a lot of options to be studied here. I just tried to go through the process step by step and eliminate all the problems I have seen during this process. That's all what I wanted to explain this time. If you like this video, I hope that you share this video, subscribe to the channel, like, comment, and other liking. It helps a lot, especially subscribing, because it increases the reach of my channel, which is something I really appreciate. And as usual, if you have any questions, you can always post them in the comments. This is the Civil Engineering Essentials channel, and we will catch you in the next video.